Well, this is up close and personal. This is a little recording of the old river dealio. Not the river, we did that a long time ago. This is the elevator deal. So forces on an elevator. All righty. So what we looked at the other day is we looked at old Bart going up and all the forces acting on this. We found accelerations. We had to find the mass of the crate first, its top speed, and then the distance we did last. We're going to do all that, but since we did the up, we're going to go ahead and do the down today. And we take a look at the graph. Now remember, this graph is a force versus time, so it'll last for less than 16 seconds. And this is the force of this scale. This scale is like a bathroom scale. But what it's going to do is going to read the force. It's going to graph the force of it pushing on the crates over time. So we already looked at the graph of it pushing up to accelerate up on the crates. Now we're going to go down, so it's going to be a little bit different, but it's the same idea. All right, let's get started here. Oh, doors are closing. Nothing's happening. Oh, it's going down. Oops. Well, still going down. And still going down, and oh, it slowed to a stop right here. So that's something to remember. So here, this is where the doors were closing. This is where doors are opening. So this is where it was stopped to begin with. This is where it stopped at the end. Those are both first law scenarios where there's no unbalanced force. So if I wanted to draw a free body diagram to help me understand what's going on here, I'm gonna try, just a minute. Get it, okay, this one, and this one, all righty. So free body diagram right over here. So this is nothing happening, so I can see the scale. This is 700, and it goes by 5, so that's 720. So the scale is pushing upwards with 720 newtons right there of force. Well, it's not moving, and there's no other forces. This is a contact force. There's no other force acting on the crates except for gravity yanking down on this thing, and that is 720 newtons. So there's no net force. Things at rest tend to stay at rest. Okay, so the acceleration is 0 for this portion. Nothing's happening. 0 meters per second. The second scenario, a little bit different. Let's change to green. And in this case, well, what we forgot to do is go back and find the mass. Let me go back and find the mass with this stuff here. Because we can find the mass, since we know the scale is balanced with the gravitational force. We know the gravitational force. We can go back, and we know we're on planet Earth. That's the other thing. We know we're on planet Earth. We can use FMUG to find the mass of the thing. So remember, this is the force of gravity over the G thing. And the force of gravity is the 720 newtons. And we're going to use, I'm going to do this quick, guys. So I'm going to use 10 instead of 9.8, and we'll see if that's close enough for my numbers to come out, just because I'm kind of in a hurry. I got stuff to do, guys. So that is 72 kilograms rather. Okay. So that's my first answer that I'm going to record, is mass is 72 kilograms. Okay, now let's go to where the forces are not balanced. So here the force is clearly about 600. I'm not going to get exactly spot on, but I'm going to try to do this as fast as I can. Now, what hasn't changed is the force of gravity. The force of gravity is still 720 newtons, the same amount. That hasn't changed. So now I have an imbalance in forces. So I can now find the acceleration. I'm going to do that right down here. The acceleration is the difference in force. And I'm going to call the up positive, the down negative. So if I do 600 minus the 720, I get a negative 120. And the mass has not changed. It's still 72 kilograms. So that means the acceleration of the elevator right there, wait for it, 120 divided by 72, 1.66666666, so 1.67 I'll call it. Okay, so the acceleration is 1.67 meters per second squared. Yes, I'm a little overdoing it on the sig figs, but I'm going to carry at least an extra one there. Then let's find the acceleration right over here. Well, here's a question, guys. We're back to this scenario. We are back to that scenario where if I do a free body diagram right over here, we have it back to 720 going upward. But we know the weight is still the same. That hasn't changed at all. That's still this 720 downward. Well, guys, things in motion tends to stay in motion. Hence, I completely expect there to be no unbalanced force there, because that's what happens when you go down the elevator. This force has to be smaller, otherwise you wouldn't accelerate downward. This one has to be smaller than gravity. So that makes perfect sense. Once you get up to speed, now the forces are balanced once again, so you're not changing speed anymore. Then again, at the end, you got to slow down. So do keep in mind, there is no acceleration for this section over here. I'm going to put it on top because I'm out of room at the bottom. So our last one to do is, how do you stop? Well, to stop as you're going down, the up force has to be larger, and that is indeed what happens. Let's go to orange here. So in this region right over here, we still have the 720 down. So that hasn't changed. That's gravity. But what has changed is the upward force. The upward force is greater than 720. In fact, it's 800 and almost 40. So we'll call that 840. Not exactly, but I'm going quick here. So now we have an acceleration right over there. And this acceleration, it's the net force. So it's the 840 minus the 720. Well, that's 120. Okay. So I got 120 newtons more up than down. That means the acceleration is going to be positive because it's in my positive direction. Sure, it's opposite to motion, but it's slowing down, going in the negative direction. That's a double negative, hence a positive acceleration. And the mass is still 72 kilograms. So this acceleration, this one was a negative. This one will be a positive 1.67 meters per second squared. Okay. So there you go, guys. That's how you can find the accelerations in each case. Now, what we still have left to do, so this is a second law scenario, and then finally at the end, we're completely stopped. So all forces are balanced once again, where we have a 720 up, and we still have the 720 down. That hasn't changed. So you're at rest there. So there is no net force. There is no acceleration. It's not going anywhere. So to find the top speed, well, the top speed is when you're accelerating downward, you got to the top speed here, and then this is a backwards force that causes it to slow down. Backwards net force of 120. The total force was 840. Okay, so your top speed is right here. That's what we got to find next. Well, we'll reach our top speed after this acceleration of negative 1.67 meters per second squared, and that's over a 2-second period. You might say, hey, how do you know that's 2-second periods? Well, remember, every one of these lines is 1 second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and that'd be 16 seconds over there. Okay, I'd show you, but I don't want my numbers to move and all that other stuff. So I'm going to leave it alone. So to find the top speed, that's your first equation. The final velocity is your initial velocity plus acceleration times time. This is your acceleration where you got to your top speed right over here. The initial velocity was indeed 0. So to find the top speed, the acceleration, sure, it's a negative 1.67 meters per second squared. And the time it accelerated was for 2 seconds. Okay. So that is 1.667. 1.67 times 2, of course, is going to be 3.33333 meters per second. So the top speed is going to be 3.3 meters per second, which is the second answer. So this is my first answer I'm going to record, which is the mass. This is my second answer that I'm going to record, which is the velocity. The last one is the hard one. It's all the displacements. It moves a distance here, moves a distance here, and moves a distance here, but how we're going to find that is going to be a little different. Okay, so I could use my second equation on this one. That might be the fastest way to find the displacement. Let me go to this blue. So where the x is the 1/2 at squared plus the initial velocity times time. My acceleration for that is a negative 1.67 Then my time I'm accelerating is for 2 seconds. Square it. My initial velocity is 0. So there would be my displacement. Okay? So it's 1/2 times 1.67 times the 4 there. And hey, I end up with a displacement of 3.3333 meters. That's only for the first section right over here, guys. For the next section, I could actually use the same equation, guys. I could use the same old equation for the next section. But see, for the next section, let me change my color here. For the next section, section number 2, it's a constant speed. So this is all 0 because there's no acceleration. I only have my velocity right there. And it has a velocity. It's going 3.333333. So if I do my 3.33333 there times the 2 seconds, that's a displacement of 6.66666666 and so on meters. So 6.7, okay? 6.7 meters. Now I have a last segment right over here where we're decelerating. Well, we could do the average velocity, which is my favorite way, but I know how much you guys love to do the long way. So what the heck, why not just do one the long way? So this is the last section right over here, the displacement there. I'm going to use the same formula. Okay, so we have a 1/2. Now this is a positive acceleration of 1.67 meters per second squared. Happens for 2 seconds. Now here's the thing, remember we're going 3.3 meters per second initially. So if I'm using this equation, I've got to use that. It's not 0 anymore. But be careful, it's going downward. So that's a negative 3.3. You got to be very careful about that. So plus a negative 3.3 meters per second times a time of 2 seconds. All righty. So I did this same calculation a moment ago, didn't I? But this is a positive one. So that would be a 3.3 meters minus 2 of those things, a 6.6, which equals a 3.3 meters. Sure, it's a negative, but technically that's a negative because we're all going downward, right? Alrighty, so let's add it up. We've got 2 of these. We've got 3.3 to 3.3, so that's a 6.6 and another 6.6. So our grand total, because this is technically a negative because we're all going in the same direction. So we basically have a 3.33 plus a 3.33 plus a 6.67 for a grand total of 13 meters. Okay, so the grand total is 13 meters when I summed up all 3 distances, the 3.3, the 6.7, the 3, and sure it's negative because we're going downwards, a negative 13 meters. But I don't think they're going to want us to put the negative in the answers. We'll find out in a second here when I slide my answers in. So I'm done with that. I am ready to end this sucker. I put my name up here, Ted. My mass is 72 kilograms. My top speed, well, that's a scalar amount. That's 3.3, so I don't have to worry about the negative there. And the distance is also a scalar amount. It's not displacement, it's distance. So that way I'm going to put in the 13.3. I'm just going to put in the 13, see if I can get away with it. That'll be close enough. And submitting. My answers are good. So my mass was a little off because remember I didn't use the 9.8. Okay, so that's why I'm a little off there. My top speed is 3.2 instead of 3.3. Once again, I rounded things, but it was still close enough. My actual distance is 15.6. You might say, hey, why the difference? Well, these little things that when I rounded off with 1 sig fig, it adds up and made it a little bit far off. But that was the correct setup and everything, and hopefully that'll help you figure out how you too could complete this task. All righty. Well, guys, have a good one. That's all for this.